Okay, good morning everyone, and thanks for coming along today. So as Debbie has said, what I'm going to be talking about today is primarily of the work that I did during my PhD. And so a few years ago, I packed my bags and I went down to New Zealand, the University of Canterbury in Christchurch, to work with my ex-colleagues here at Mike Spearpoint and Charlie Fleischman. So it's an overview of that work. It was done, completed like nearly 8 years ago now, so you're probably saying, oh, why are you telling me stuff that's that old? What it is, this work is now being implemented in terms of British standards and guidance, and in terms of zone models, and it's about to hit the streets, and it's actually relevant to you now, so it's quite an apt time for a revisit if you've heard this before, or even for the first time that you've seen this work. So again, credit to University of Canterbury, because I acknowledge them in this work. It was the work done there. Okay, it's related to the smoke control and spill plume design. I'm not really going to be touching too much on the details of smoke control, but there are several objectives in carrying out smoke control design that you may need to consider. It may be that we are removing smoke from a building to create a clear layer for safe means of escape. Alternatively, it could be providing or maintaining tenable conditions in the area of fire origin or in areas adjacent for means of escape. Another objective is removing smoke during or post-firefighting operations, or minimising the risk of smoke spread to adjoining parts. So there's various objectives specific to a particular design. But today I'm really going to be focusing on the thermal spill plume in smoke control design. Just to give you, here's a drawing of a thermal spill plume to give you an idea of what this actually means. When it means a thermal spill plume, it's really hot gas rather than flames and from a post-flashover fire. But generally, you'll find a spill plume being generated for a fire, say in a shop unit or an office unit. Smoke layer then forms within that unit itself, flows horizontally, perhaps underneath a downstand, perhaps then beyond a balcony, and then spills and rotates at what we call the spill edge here, and rises as a plume, entraining air, and then either forming a smoke layer which may be exhausted or there may be smoke filling. The key here really is the amount of entrainment that occurs into the plume as it rises. So for all of those methods that I've described earlier, you would normally determine the mass flow rate in that plume, and that is dependent on the amount of entrainment. Now, I think it's quite important to talk about terminology and make it clear the terminology that I'll be using today, because different people use different terms. Essentially, there are two generic types of spill plume that are available in design. On the left-hand side here, we have what we call a balcony spill plume, which I've effectively just shown, fire in a unit, fronting onto a larger space. In this case, we might have a balcony projecting beyond the unit itself, flowing beneath, and then rising as a plume. And in a typical case with a balcony spill plume, the plume actually projects beyond that opening, rises, and you'll get entrainment into the sides here and into here as it rises, and that's really key to this. Some people may call this a double-sided plume, but today I'll be referring to it as a balcony spill plume. The other type of plume is called an adhered spill plume, which you see here on the right. In this case, you'll have a unit, but you'll have a wall projecting above that spill edge. And typically what you'll find is as the layer forms and rotates, it adheres and sticks to the wall as it rises. And there you would get entrainment into one side of this plume as it rises. There'd be less entrainment typically for an adhered spill plume. Now today I'll be talking about 2D plumes and 3D plumes. So when I talk about 2D plumes, I'm talking about plumes that actually do not include entrainment into these ends, that's into the screen. That's if you've got a plume that's bounded by walls. Not that common in design, but can happen. So a 2D plume would not include entrainment into these ends in both cases. What's more common in design is through a three-dimensional plume, and that's having entrainment into these ends, and in this case, into the sides as well. So they're the two types of plume that I'll be referring to today. Now, there are various calculation methods that are available to the fire engineer in terms of calculating entrainment into plumes. There are generic types. The first of these is a simplified spill plume formulae. I love these. These are really good. So these are typically based on empirical correlations from experiment. They're commonly used in design. You'll find it in CIBSE Guide E, PD 7974 Part 2, and FPA 92. Single one-line equations, typically applied for relatively idealized designs for what you've seen here in terms of the drawings previously. But they're also useful in the early stages of design as well for more complex geometries. It gives you a starting point. If you're going to do use more complex methods, what do you do? Guess? You need to actually base it on something as part of an iterative process. And it's really this type of formula that I'm going to be focusing on today, because we've produced a new suite of formulae on this in this particular piece of work. There are also other methods, such as analytical method or theories. There's the BRE spill plume method, which was developed here a number of years ago. There's the curved plume method, again developed at BRE by Suresh Kumar and Jeff Cox. And there is some new work, again, on the theoretical appreciation of spill plumes. I won't be touching on that too much today because I simply don't have time, but I can talk to people afterwards about that as well, because there's a lot of findings from this work. There's also the use of computational fluid dynamics modeling, again more versatile than the simple models, and can be used for more simple or more novel designs rather than simple designs. But at the time this work was done, there was very little validation of the spill plume in terms of CFD modeling. So in terms of the drivers for this work, there are a number of uncertainties and limitations in some of these calculation methods. The supporting experimental data, certainly for the empirical correlations, was particularly sparse. In some cases, just a handful of data points. That was all that was there. And you could get large differences in the smoke production rates between different formulae that are out there, all predicting the same thing, but very different results. Which one do you use? And there were simply scenarios where guidance did not exist at all, and that's something that I've tried to build upon and increase and provide more options to the fire engineer. So in terms of the aims and objectives of the work, again, quite a simple objective was to provide a better understanding of spill plume entrainment. What are the processes that are going on here? What do we need to consider? But the objective was to provide new data, essentially, from an extensive number of experiments, and it's to provide options, really, to fire engineers in spill plume design. So I've looked to develop a range of new and improved simplified formulae for a variety of different spill plume scenarios, improvements to the existing analytical methods as they use empirical elements in terms of the entrainment coefficients. And I also carried out an initial assessment of CFD modeling and recommendations for appropriate grid design for fire engineers as well. So I'll be touching on these points today, but again, in the 20 minutes I've got, I simply can't go into any great detail. In terms of the approach they took for this work, the vast majority was based on physical scale modeling. Something that I cut my teeth on here at BRE many, many moons ago. And again, this is my time in New Zealand. It was a bit of a busman's holiday, really. It was building on a lot of the knowledge that I had gained here at BRE. So it's using physical scale modeling. In this case, it's using scale model fires themselves, and we use here a number of alcohol fires in a 1/10 physical scale model. It's very important when you're doing physical scale modeling to get the design of the rig appropriate and the size of the fire right, so you get turbulent flow on both full and model scale. It's a well-established technique in smoke control research. So we would measure things as temperature, velocity, mass flow rate, and I carried out over 300 experiments in the time at Canterbury, so a much, much bigger data set than was possible previously. And it's given this data set to understand spill plume entrainment more in more detail. Just to give you an overview of some of the photographs here. So here we've got our fire compartment, as you'll see it below here, generating a fire. It's just industrial methylated spirits fire. It really doesn't produce any soot. It's basically just hot gas and CO2. And what we do is we inject theatrical smoke into the hot gas layer to visualize the plume and the layer itself. There's our compartment. We have a collecting hood here. to collect the spill plume and measure the mass, and then we've got an extract duct with a mechanical fan here, so we can raise and lower the layer and look at different heights of rise, and different widths of opening as well, from wide shop units to doorway openings. And there we just see the rig in action, and we've got a balcony here and a balcony spill plume being generated, collecting the mass flow rate of smoke and measuring that in terms of entrainment. Here's a photograph of an adhered plume. Here's our fire compartment, the smoke layer forming here, rising and adhering to the wall, and we've got entrainment occurring into the plume on one side. Here's the equivalent for a balcony spill plume. You'll see here, projecting, there's our plume, and we're getting entrainment into both sides, and in this case, into the ends. So it was a busy time looking at quite a number of different scenarios. Now, to supplement those experiments, I carried out some numerical modeling, and this was using Fire Dynamics Simulator. Here we see a simulation of the experiment. We used CFD to model this experiment, and it gave a good prediction of that. I'll come to that in a moment. But it also enabled me to look at spill plumes for a much higher height of rise than were possible in the experiment. When we scale this up, I was managed to go to around a height rise of around 10 meters. I couldn't physically reproduce anything greater than that in the lab, but here we looked at spill plumes again, 50, 60, 70 meters for a particularly large building to see how those plumes behave. Just to note, this work was done, finished 8 years ago, so FDS 5 was used at that time. I know things have moved on, we're now in FDS 6, but I'll come to that in a minute in terms of the applicability of this work. Okay, just a little bit more about terminology, because you're going to see some equations in a minute. I'm not going to get too heavy on the equations, but it's quite important to show you what the terms in these equations actually mean. Got a photograph here looking into our fire compartment from one of the experiments. Here's the fire. We've got potentially a shop unit here. This is the equivalent of around 10 meters wide on full scale. We've got what we call channeling screens, which are often used in smoke control design in shopping centres to channel the smoke out. And then we've got our plume and our layer forming and our plume rising. So you'll see the terms WS, which we have here. That actually represents the width of the spill plume from the shop. It can be wide, it can be narrow. DS, which is the depth of the layer at the spill edge, just before it spills and rises. ZS, which is the height of rise of the plume above the spill edge at the point where it may meet the layer, or depending on where your design layer height is. And then we also have Q.C and M.S, which is effectively the convective heat flow in the layer as a whole, as it gets to spill, and the mass flow rate in the layer. It's the source term, effectively, of the spill plume. It's a very important key parameter, an input parameter in working out spill plume entrainment, but it's over that region just before it spills, the source. In terms of the experiments, again, as I've said, over 300 were carried out. I varied the fire size, the compartment opening. This is the equivalent of around 10 meters wide. This is more like a doorway opening, around 2 meters wide. The plumes look quite different, that you notice. Also looked at 2D and 3D plumes. If it wasn't clear what I meant by 2D plume, here's a photograph of one of the experiments. It's got some sidewalls here, channeled all the way up to prevent smoke getting into the ends, but they still get in the sides. And we looked at balcony and adhered plumes as well. Okay, I'm going to show you some data. I just love plotting data and trying to get the best out of it. I don't want to get too academic today because the axes are plotted in a particular academic form that you would expect for spill plumes and for line plumes. For you today, you just really need to know that the horizontal axis increasing really represents the height of rise of plume as it rises above the spill edge, and the vertical axis is the increase in mass. That's all you really need to know. When you plot in this form for spill plumes, there is linearity exhibited in the data, and we see that here, so we get a straight line. Just to note that the slope of that straight line represents the rate of entrainment with respect to height. Shallower slope, less entrainment, steeper slope, more entrainment. So I plotted this data as a whole, and no one had really done this before. All previous experiments that had been done had effectively been done on one width, one scenario, one line. There's some scatter here, but generally it's showing linearity in the data. And I could have actually put a line through this, averaged it, and just got a single equation. But we can do better than that, because when we look a little bit more closely, if we look at the crosses here, you could put a straight line through those data points. The crosses represent a wide shop unit. If we go to the diamonds, for a narrow one, we're looking here, we can get something that's represented a line through there as well. And if you look at the data points in between, there are families of straight lines. So for a wide unit, it's a slightly shallower rate of entrainment. For a narrow unit, it's a steeper slope. And we could have had a whole family of linear relationships here and said, well, if you've got this particular geometry, choose that line. Didn't want that either. I wanted something that was actually a bit more versatile and that could be used more generally. So I'll come to that in a moment, how we did that. What I'm just showing here next is some existing guidance. How does that compare with this data that was actually produced? You'll see that NFPA and CIBSE guide guidance and PD 7974 Part 2, quite a higher slope. It actually matches the data from the narrow compartment openings. And this is an equation I developed when I was doing my master's course back down in New Zealand as well, which is generated from a slightly wider compartment unit. That matches the data from the wider units here that I was looking at. So it became quite clear that the existing guidance that was out there was not incorrect, but it was actually quite specific to the original experiments from which they were derived. And I'm not going to criticize anybody for the older experiments because it's based on a very limited amount of data. So the objective here was to get a single equation which could represent all of this type of behavior. It's not a panacea, I'm not going to say that, but it's certainly an improvement to give you that range. So if you're a designer previously, before this work, which one do you choose? Do you go for an FPA 92 or go for the maximum amount of entrainment? If you're looking at tenability, that's not on the side of safety because you're predicting more mixing. But if you're looking at clear layer height, that's the way to go. So it's not quite obvious which is the worst case here. It's not always the one with the steepest slope. Let's try and get something that's a little bit more applicable and generic. So I'm not going to go, as I've said, into the real academic detail. All the papers are there. I can chat to you afterwards about it. But essentially, the approach that was done here was to develop a general expression. And this was done by decoupling and characterizing the key entrainment regions. And the key entrainment regions effectively are the mass flow rate and the heat release rate in the flow below the spill edge. There's a 2D region above the plume itself, and we could characterize that. I did that by looking at 2D, because I separated them. And then we've got what we call the ends, entrainment into the ends. And I managed to characterize these all separately, and then plug them all together to give a more generic equation that represented a whole range of entrainment rates. And when you do that, that experimental data that you've just seen collapsed to a single relationship, which is great. And I think when I got to that point, I think I got enough for my PhD at that point. So it was a good marker when I was doing this work. So this is what you're going to see in terms of guidance. And there is other guidance out there, but in terms of this work. I haven't really talked about the 2D plume because I haven't had time today to do this. But here we have an equation for the 2D plume, and this one is for the 3D plume for the balcony spill plume. Just two simple formulae. For your information, this part of the term relates to the amount of entrainment above the spill edge, and this part is below. And we've got something similar here for the 3D plume. But we've also got this term that relates to the width and the depth of the spill edge below the balcony. This is the key to the amount of entrainment. So what you'll find is for a really wide shop unit, so you've got a big shopping mall, you've got 20, 30 metre unit width, you'll find that the width dominates and depth is actually quite small for a design fire. So this is insignificant, this dominates, it becomes more like a 2D plume. But for a very narrow doorway opening, this is more significant and you get more entrainment, and that's really what the difference is here. And that's how it's been built into those two equations. Okay. Again, carried out some CFD modeling using FDS, carried out a grid sensitivity analysis to model the scale model. And what we've got in terms of my thesis is there is some guidance on an approximate grid size, a non-dimensional grid size using FDS5. I found that FDS5 gave very good prediction of spill plume behaviour, both for adhered plumes and for balcony spill plumes. So this gave me the confidence to use numerical modelling to look at plumes of a much higher height of rise than were possible in the experiment. Okay, as with any equations that you develop, there are limitations. Now, you've seen from that data set there is linearity in those equations, and those new equations exhibit that. But we do know that the spill plume will behave in a slightly different way as it gets higher and higher. You can do dimensional analysis. There's been a paper by Philip Thomas on this, on a theoretical analysis, that it won't behave in a linear relationship forever. There will come a point where it breaks down, and it actually behaves more like an axisymmetric plume, a fire in the open, which is more like a power law. So I knew this would occur, so what I did is it's quite a simple analysis. I've taken my spill plume equation, and I've taken an axisymmetric plume equation. I've equaled them together, I've matched them, and I've come up with what I call a transition height. So this is the limit on the use of my equations that you've just seen, Z trans. And this gives us the point where those equations break down in terms of linearity, and beyond that, it becomes more like a power law, and that's when you should stop using that equation and use something else. So if you've got a height of rise that's above this transition height, then you should be calculating entrainment more like an axisymmetric plume that you see here, and this is just standard that you'll find in PD 7974.2 or in FPA or just generic guidance around the world. So that was an approximation just based on matching those. So I carried out actually more analysis using CFD just to try and, well, not validate, but investigate this finding. So what you're going to see here is basically a plan view and a snapshot just showing the shape of the plume with respect to increasing height of rise. So here we have very low down, close to the balcony itself, snapshot across the plume, quite long and thin. But as we see it, as we increase that height of rise, as the plume rises, the nature of that plume is starting to change and it's becoming more axisymmetric in nature, just as the dimensional analysis would suggest. No one had really looked at this before. So it was getting a feel for when that transition occurs. And here's some data that I've actually produced. This is just the full scale equivalent in terms of height of rise of plume, and this is increase in mass. So the full scale equivalent, and this is for a width or a shop unit that's only 2 meters wide. So it wouldn't be a shop, it would just be perhaps an office or whatever, a doorway opening. What we have here, the red dashed line, is the linear equation that you've just seen based on the experiment. So up to a height of rise of around 15 meters above the spill edge, you'll get in a reasonable approximation, again matching by the FDS prediction of this equation. But you'll see beyond this, it's starting to depart. So FDS is showing that it's actually behaving more like an axisymmetric plume above that height. So if you were to blindly use my equation, again up to these heights of rise, say it was 40 meters, I know that's a very high height of rise, you'd be under-predicting entrainment really by about another 30%. So it's important to have that limit of when to use these equations. Now, because this is quite a narrow opening, it's more square when it actually comes out underneath the spill edge, so it tends to depart earlier or a lower height of rise. Here's the equivalent for a wider shop unit, for a 10-meter wide shop unit. You see here it's now, again, adhering to this linear equation for a much higher height of rise and then just starting to depart here. And what we found is, in all the work that we've done, is that simple approximation that I've just developed actually shows that the departure occurs at that point. So we've got confidence when to use this equation. which is great, because you always need to know the limits of your equations when they work. Okay, moving on very quickly now to the 3D adhered plume. Won't talk about the 2D today. Move on a bit quicker. I've got 3 photographs from the adhered plume scenario. As I showed earlier, typically they adhere to walls. From this work, actually they don't. Here we've got the case where it does. So we've got a wide opening here, 10 meters. Here's our fire compartment, side-on shot. Out comes the plume. Here's a wall above that spill edge, sticking to that wall, entrainment into one side. That's typically what we would expect. When we have a slightly narrow opening, this is 6 meter wide, what we find is that the layer then projects slightly beyond this opening. There's more horizontal momentum or velocity. But what you get some mixing behind, and you get warming of air behind. This is called the Condor Effect. That warming creates a negative pressure. It's either the plume itself, or as it rises, tends to get pulled back, and it adheres back to the wall here. So you get this area where air is being entrained sort of into the screen and into the back of the plume. So there's more entrainment here than here. And if you go narrower again for a doorway opening, actually you don't get it adhering at all. It behaves a bit more like this balcony spill plume. It's projecting, not adhering, and we're getting clear air into the back because it's quite a narrow width. The air doesn't have to travel very far. So the conclusion here is, depending on the geometry for a 3D adhered plume, you get quite a different entrainment region and behaviour. So I thought I'm really going to struggle here to get a single equation representing all of this. Again, here's the data. Same thing, increasing height, increasing mass. Without going into too much detail, it's the same type of behaviour. There is more scatter. We're attending more entrainment for the narrow plumes because they're projecting per unit height of rise compared to a wider plume that sticks. Again, I use the same method in characterising different entrainment regions. And amazingly, this data collapses down to a single relationship as well. Perhaps I just got lucky, I don't know, but it works. It works. And these are the equations, both the 2D and the 3D adhered plume. You notice here, if you looked closely previously, for the 2D plume, as the balcony plume, it was 0.16. Roughly, you'll find 0.08. It's roughly half the entrainment. But this equation encompasses all of that behaviour that you saw previously as well. So we've got some improvements on what we originally had. Just to note, I also carried out FDS modelling of the adhered plume, and we're getting the same behaviour, adhering, projection, and then projection here. So we've got some confidence there that FDS can predict this type of behaviour. Everything I've done so far in this work, or talked about, actually related to small-scale data or modelling. I'm very lucky that nearly 20 years ago, and there's colleagues in the audience today who carried out some hot smoke tests in Brussels. This is the European Parliament building. This is over 20 years ago. We did a full-scale hot smoke test of a fire in an atrium. And here is Brussels Airport. That was done even earlier. That was back in 1994. And this is a balcony spill plume. So I had confidence in the data that we produced from this work, and I was sure as hell going to use it to give some confidence in the equations. What I found was my new equations gave a very good prediction of both of these experiments in the hot smoke test, and we got some excellent agreement as well, using the FDS modelling, using the grid size and such. So that's given me some confidence that if we've got some full-scale data as well, if not very, very limited. So just to say that this work is now being implemented at the moment. It's in the current draft of CIBSE Guide E. Next revision, I think it's coming out probably in the next couple of months. I think it's definitely coming out this year. It's included, these equations are included within that guidance. I'm currently leading the panel of PD 7974 Part 2. Just gone through public consultation. We had a meeting last week dealing with the comments on that. We're hoping to have the next revision of that end of this year. Again, this is coming your way. And I've also talked to effectively the European Standards Committee as well, and it's going in to there. So it is being implemented quite widely. Another area that we've included this is in BRIS, the zone model BRIS. Some of you may have heard of this. More people may have heard of the zone model Brandsfire. So I was working with the engineers at the Building Research Association of New Zealand, They didn't used to have a spill plume model in their zone model. We've now included it in BRE, which is the next generation version of that. It's in the user guide, and then we produced a paper in fire technology, again peer-reviewed to show validation of its use. So we have a simple form, we have it in zone models, and I've also been working with Kevin McGrattan at NIST, who's used my data in terms of validation for FDS6. So I know everything I've talked about before was FDS5, but it works as well for FDS6, and this comes from the validation guide for both balcony and adhered plumes. And yeah, they were very happy when they received my data for this because, again, FDS worked really well. So it's been implemented really across the board, which is really great because I didn't really want my PhD thesis to sit gathering dust on a bookshelf somewhere. You don't have to read these next slides. It's just important that we publish widely and it's peer-reviewed. There are a lot of other issues that I've looked at, like unchanneled balcony spill plumes. I've looked at smoke contaminations of atria and upper balconies with a master's student at Canterbury. But just to make you aware, and I can give you the details afterwards, there are a number of peer-reviewed papers and even more. So it's there. It's got the robustness, and that has been peer-reviewed. At that point, I'll probably stop. Just an overall is a summary in that we've had a range of new guidance has been developed in terms of simplified formulae for both balcony and adhered plumes, a simplified formulae for when a balcony spill plume becomes axisymmetric, an assessment of numerical modeling, and all of this is being implemented now, and it's about to hit the street. So it is relevant to today, even though it takes a long time to get research into standards and guidance, I'm afraid. But yeah, again, that's relevant. So thank you very much. I think I'll stop at that point because I think we're going to go for tea.
So thank you for that, Roger. The one area that you're not feeding it into yet is ISO TC92.
Yes.
Subcommittee 4.
I'm so busy. We'll do that next on the list.
Is there any questions for Roger? We got time. There's one up the middle at the back. Thank you.
Bob Birtles, Great Manchester Fire Service. Do normal atmospheric conditions impact on the behaviour of the plume, like temperature, pollution, humidity?
Typically, the fire size is in there, but typically we're looking at temperature above ambient. So I did my experiments over a range of months and different background temperature conditions, but usually it's the temperature above ambient in terms of the buoyancy. So typically not. And things like humidity, I think it's probably insignificant, really. And
what about the type of smoke? If it's like
well, when we do this, we treat smoke as effectively as hot gas, because that's effectively what it is. There is no way we can distinguish between different types of smoke. That's the way that's done in those sorts of analysis. It's a hot smoke analysis. The type of soot that yield as such is buoyant within there, but in terms of the entrainment process, it's not deemed to be particularly significant. And yeah, again, we've done this, and I've looked at that full-scale data from. I know that was only theatrical smoke, but it tends to work in that case. So that's the way we treat all smoke control calculations, because we can't actually predict necessarily exactly how that is actually produced, but I don't think it's that significant.
Okay, so with that, if you've got any further questions for Roger, please track him down either at lunchtime or the networking break.